This is FRM Part 1, Book 2, Foundations of Risk Management, Chapter 8, Linear Regression with Multiple Regressors. You should remember in the previous chapters that we focused on a simple linear regression in which we had one independent variable explaining a dependent variable. And so this chapter could be called, hey, if one variable is good enough, why don't we add a bunch more? So we're going to have multiple independent variables on the right-hand side of our regression equation. And what this is going to do is A, add value to understanding what goes on behind the variability in the dependent variable. And then the second part is that there are going to be some consequences of adding. And so, like I teach my children all the time, there are marginal costs and marginal benefits with adding extra independent variables. So let's look at the learning objectives here. We're going to start by looking at some omitted variable bias. We're going to distinguish between single and multiple regression, which I just did a little bit there. We're going to do slope coefficients, which we did in the previous chapter, talk about homo and heteroskedasticity, describe the ordinary least squares estimators, and talk about measures of fit, talk about the assumptions, and then we need to worry about multicollinearity, which is something that we ignored, which we could ignore back in a single regression equation. So let's get right to the omitted variable bias. Now remember what we're doing here. We're trying to develop a regression equation in which we can explain the variability in the dependent variable. So what we want to do is we want to come up with, how about if I call it a perfect model in which we have a bunch of variables on the right-hand side and they perfectly explain the dependent variable. How often are we going to get that? How often do we ever get perfection in life? Of course, it rarely happens. I mean, sometimes it happens, but it's a rare event. And so one of the big challenges in multiple regression analysis and the interpretation of the results is, do we have the right model? If we don't, if we're missing a variable, we call this the omitted variable bias. And this occurs, are you ready for this? Now this is really cool from a statistical standpoint. If the omitted variable is correlated with the movement of independent variable in the model, and the omitted variable is a determinant of the dependent variable. So omitted variable bias occurs when there's a relationship between and among the independent variables, and then if there is a relationship with the dependent variable. All right, so what happens if we have omitted variables? There's violations of the linear regression assumptions. We underspecify the model. That should be self-explanatory. And then our estimates of the intercept term, which becomes less and less important when we have multiple regressions, but the slope coefficients are biased and inconsistent. Remember in that last end of that last chapter, we talked about blue. Well, when there's omitted variable bias, there's none of that stuff. So let's look at an example here at the bottom of this first slide. If we're trying to explain GDP growth against things such as, boy, we had interest rates in the last chapter, but let's add inflation and exchange rates. And then leaving out one or more of these variables would result in biased estimates because there's that interaction on the right-hand side of the regression equation. All right, one way to do this is to perform the Ramsey test. And this is a product of lots and lots of software programs that you can relatively easily perform. Now, if we find that we have an omitted variable bias, what we can do is divide the data into groups and then examine one factor at a time while holding other factors constant. Now, I remember being in graduate school when all of us were trying to use regression models to explain certain dependent variables, and the easy way out was always, just add a bunch of more variables and see what you come up with. But that's really not the way to do this. So good statisticians, good econometricians will incorporate multiple fundamentally relevant and sound independent variables in the model so that the significance of each variable can be tested. And we'll do that in just a little bit. All right, there's the single regression model that we talked about in the previous chapters. Beta 0 and beta 1, those are the regression parameters. Remember, those are unknown. There's our y and our x variables, and then there's an error term. Multiple regression simply adds some extra explanatory variables that will help, or at least theoretically help, explain the variability in the dependent y variable. What did we have in just that previous slide? We were trying to explain changes in GDP. We started with interest rates back in the previous chapter. And then what did we add in that slide? We added some inflation measure. We added maybe exchange rates. We could add maybe some measure of who's in charge of the politics of a particular country. Maybe oil prices, maybe manufactured goods growth. There are lots and lots of variables from which to choose. There's the multiple linear regression model. And so note that there's a beta 1 and a beta 2 all the way out to a beta k. What that means is that we're trying to determine what is the sensitivity, what is the slope of that one independent variable while holding, are you ready for this? While holding all other independent variables constant. Now the process by which the intercept term and the slope coefficients are computed is the same thing as what we did in the previous chapter. What we're doing is we are going to minimize the sum of the squared error terms. But instead of having the sum of the squared error terms be like this big with the simple linear regression, with multiple regression, we got a big old matrix. But again, the good news, of course, and I bet you guys know this, that tons and tons of software programs do this. All right, so what we're doing here from the top, that's our theoretical model in which we define the x variables as being economically and fundamentally and theoretically sound independent variables that are able to predict that dependent variable. And so we use this OLS method, which minimizes the sum of the squared error terms, and then we result with those estimates there at the bottom, and note that there are a bunch of hats on the y's and the beta variables. That just means that the intercept term and the slope coefficients down below are unbiased estimators of the true values in our model at the top of the page. All right, some of the assumptions for multiple regression are identical to those from simple linear regression. The relationship between the dependent variable y and all the independent variables is linear. I mean, that makes perfect sense, right? We're going to draw a line. When we minimize let me go back here. When we minimize the sum of the squared error terms, that's what we're doing. That's the line is the result of that minimization. Independent variables are not random. There is no exact linear relation between two or more of the independent variables. So on the right-hand side of that multiple regression model, you can't have two variables that are highly correlated, right? Because if they're highly correlated, then they have a relationship. They're not independent. And so if they're perfectly correlated, and we'll talk about this in a few slides, if they're perfectly correlated, you have two variables who are trying to explain one variable, and if they're perfectly correlated, then you don't need both. That sounds an awful lot like misspecification. Expected value of the error term, once again, is 0. The variance of the error term is constant, of course. The error term is uncorrelated across observations and is normally distributed. And I remember when I first learned this back in graduate school, I remember thinking those last couple of assumptions, boy, they probably weren't too terribly important if they were violated, and boy, was I ever wrong. They're extremely important. All right, let's take a look at our example. Once again, from last chapter, we have GDP growth, and then on the right-hand side, we're going to have some measure of interest rates, but then we're going to add a second independent variable. Let's call this a measure of inflation. So we're going to use 30 observations, and we go into Excel or some other software program, and we get coefficients. So there's the intercept, 0.3, interest rates 20, and inflation 15, and the standard errors are over on the far right column. So how do we interpret those rates? So what we're saying here is that the intercept term, if the interest rate is 0 and inflation is 0, we would expect the growth rate to be 3%. The interest rate coefficient, if interest rate increases by 1%, we would expect GDP growth to increase by 0.2%. And we would expect inflation to increase by 0.15% while, and notice the underlying there, that's important, while holding inflation constant for the interest rate coefficient, and then while holding the interest rate constant while looking at the inflation rate coefficient. Now there's homoskedasticity. That's one of those assumptions. And so notice the beautiful picture there on the left. The error terms, all those dots, if you look at the variance of all those, that's probably constant. I mean, they look like they're all about, on average, about the same distance from the line. That's called homoskedasticity. But if the variance of the error terms is not constant, as clearly evidenced by that right-hand graph, where they kind of look like, you know, someone's speaking in a megaphone and we're shouting out to the right. And it doesn't have to be to the right. Those differences could be to the left towards the origin, or they could be somewhere in the middle. But clearly there's not a constant variance, and that's why we have heteroskedasticity, and then that's going to cause the same problems that it did back in simple linear regression. So it can be caused by omitted variables, and it can be caused by outliers. Now remember what I said back in the simple linear regression chapters is that the R-squared is a measure of accuracy. But with one independent variable, it's pretty hard to get a high R-squared. I mean, you think about it. If you're trying to measure the changes in one variable by measuring change in just one other variable, that R-squared, which remember is correlation coefficient times correlation coefficient in a simple linear regression, it's hard to get a big one. In fact, in graduate school, when we were estimating beta for individual shares of stock, we just use the single index market model with the returns on the market portfolio and the returns on an individual stock. Our squares are like 3 or 4%. And my econometrics professor would say to us, who cares about R square when we're doing that model? Because there's only one independent variable. But now when you add independent variables, you ought to expect the accuracy of that regression equation to increase. All right, so that's what R square, this coefficient of determination, it's a measure of the goodness of fit of the regression equation. And this is my way of interpreting R square. It's a measure of the percentage of variation in the dependent variable that can be explained by variation in the independent variable. And there's a good formula there to memorize at the bottom of the page, just like it was back in simple linear regression. Now, let's take a pause here. Let's take a pause here and remind ourselves that with the simple linear regression, if R squared is 1, that must mean that the correlation coefficient is 1. That's perfect correlation. Now, here's the problem with R squared. It's not very reliable. In fact, it has been shown by tons and tons of researchers, including young and naive researchers like I was and my colleagues were when we were in graduate school. You could just add variables to the regression model and it would increase the R squared. But of course, statisticians are really, really smart. They know that R squared is not reliable, so they adjust it. And we always make an adjustment for degrees of freedom. All right, so R squared almost always, there's the almost word in there. In my experience, it almost always, I think it always did whenever I used multiple regression models, almost always increases as new independent variables are added to the model. Even, you ready for this? Even if the marginal contribution is not statistically significant. So you can just throw variables in there and get a higher R squared. So notice that second block point there. A high R squared may reflect the impact of a large set of independent variables rather than how well the set explains the dependent variable. And so that's why we adjust the R squared. And notice what I said there in that last slide, that we adjust these for the degrees of freedom. So n minus 1, n is number of observations. and then n minus k minus 1. K is the number of independent variables, and so you really just are adjusting for degrees of freedom. And that adjusted R square is not going to automatically increase when n gets larger. Here's a quick example here. Let's suppose that we look at some monthly stock returns, 4 independent variables over 48 months. There's some output, calculate R square and adjusted R square. So in this case, the R square turns out to be about 67%. The adjusted R square turns out to be about 64%. But let's now suppose that we just simply add 4 more independent variables to the regression equation. What happens? If the new R square increases, so where were we? We're at 67%, so the new R square increases to 69%, but the new adjusted R square, notice what's happening here, oh my goodness, it used to be 64%, now it's down to 62%. So looking at adjusted R square from before and after more variables are added to the regression equation kind of gives you a sense of whether or not those extra variables were important. And it gives some insight as to whether or not they will be significant when we perform one of those t-tests. All right, let's start at the extreme. I always like to go to the extremes. I learned this from back in calculus when you come up with corner solutions. And so if you know what happens at either end of the spectrum, then what makes sense in between is a little bit more clear. So perfect multicollinearity is a violation of one of the assumptions. All right, so you can't have a relationship between 2 independent. Remember, they're supposed to be independent. All right, perfect implies that the variation in one of the explanatory variables can be completely explained. And so there's an example in red where there's no error term, so it's completely, perfectly explaining x2 is explaining x1. And then there's a picture of it. x2 and x1, they fall directly on that line. There is no variability at all. So what are the consequences here? So ordinary least squares is not capable of generating estimates of regression coefficients. I mean, most of these programs will print out a message that says, you know, dear Jim, what did you do by selecting these independent variables? Go back to your very first stats class and fix the problem. What it does, it ruins our ability to estimate the coefficients because those variables cannot be distinguished from each other. So that whole thing that we talked about in a previous slide about holding one other independent variable constant, it just can't happen mathematically. So of course, this is misspecification, and you just drop one of those variables. Now, imperfect multicollinearity, I mean, this occurs pretty regularly. So when they're imperfectly linear correlated, and look at that graph there at the bottom. I mean, clearly x1 and x2 are related to each other. As x2 goes up, x1 goes up, and as x1 goes up, x2 goes up. And so there's going to be a linear function if you regress x1 on x2 or x2 on x1. And that's a violation of that assumption. All right, so how do we detect multicollinearity? Well, high correlation among independent variables suggests the possibility, but remember, low correlation does not necessarily indicate that multicollinearity is not present. Now here's the deal. Some multicollinearity exists in every equation to some degree. I mean, think about our example that we just had. Changes in interest rates, right, and then changes in inflation. They're supposed to be completely independent. The assumption is that means that their correlation coefficients have to be 0. But clearly, when inflation goes up, interest rates go up. And so we need to be worried about what is the degree of that correlation. All right, so here are the consequences, and this is probably the more important part of this learning objective. Estimates will remain unbiased, so the estimates is not a problem. However, the variance and standard errors will increase because it's harder to distinguish the effect of one variable from the effect of another, and so you're probably more likely to make large errors. What that means then is that the t-scores will fall. So if the t-scores will fall, you have much less of a chance of rejecting the null hypothesis. The fourth consequence is that those estimates will become very sensitive to changes in specification. In other words, if you add another variable, or if you drop a variable, or if you take the natural logarithm of a variable, it completely changes the output. Change dramatically. Now, the overall fit of the equation and the estimation of the coefficients of the non-multicollinear variables will be largely unaffected. And that takes us through Chapter 8. We'll continue this discussion with some more multiple regression slides.